Okay, we're going to do one more applied optimization problem here. And you may have done something like this in an algebra class before arriving in this calculus course. But we're going to set up an equation and use the derivative equal to 0 to minimize Jane's time. So Jane is 2 miles offshore in a boat, and she wishes to reach a coastal village which is 6 miles down a straight shoreline from the point nearest the boat. Jane can row 2 miles an hour, and she can walk 5 miles an hour. What we need to determine is where Jane should land her boat to reach the village in the least amount of time. So I'm going to set this up. I'm going to draw a picture here. We have a shoreline, a straight shoreline. And we know that Jane, she's offshore here. She is 2 miles offshore. Okay, so we know this distance is 2. And this is a possible landing point on the land. I'm going to call it L. And what we know is she wants to get somewhere to this village, which is 6 miles from the point directly perpendicular to land from where she is. So, Jane has a couple of options. Her first option would be to row straight to shore, disembark her boat, and then walk 6 miles to the village. Okay? Her other option would be to row straight to the village. And then a third option would be to row her boat, land somewhere on the shore, and continue to the village. So what we're going to determine here is where should she land so that she can get there as fast as possible. So let's think about these situations. If Jane were to go 2 miles directly to the shoreline and then 6 miles to the village, she would be traveling 2 miles at 2 miles per hour, which is this distance right here, and then 6 miles, and her speed at walking is 5 miles per hour. So 2 miles at 2 miles per hour is going to take her 1 hour, plus 6 miles at 5 miles per hour is going to take her 6/5 of an hour. So essentially, if she's to take that route, Jane is going to travel for 2.2 hours. So that's one possible option for her time. Also, Jane could row directly along this hypotenuse to the village. And we can determine the length of that hypotenuse using the Pythagorean theorem. And that would be the square root of the square of both sides. So 2 squared plus 6 squared, which is 4 plus square root of 40. So, or she has the option to row the square root of 40 at 2 miles an hour. And the square root of 40 simplifies to, we can simplify that radical there and get 2 root 10, because I know the square root of 4 is 2. So 2 root 10 miles at 2 miles per hour. That's going to be 2 root 10 miles divided by 2 miles per hour is the square root of 10 hours. And square root of 10 is approximately 3.16 hours. Okay, so that is clearly not going to be the fastest. But what we have to look at, 2.2 hours is what we have found if she just rows directly to the shore and then walks. So we need to consider this third option where she lands at some point on the shore and then continues her path walking. So I'm going to continue this problem and give us some more space here. We're going to redraw our options. Okay, so we have from J, I have point L and I have point V. We know that is 2. We know from L to V, all of that is 6. And we're going to assume that maybe we land at some point P. So Jane's path here is going to go to P and then to V. Now when she's traveling from J to P, her speed is 2 miles per hour. And when she's traveling from P to V, her speed is 5 miles an hour. So we need to figure out how to label these lengths. So one of my first options would be to, start using variables. I do not know how far downstream she's going to be. So from L to P, we're going to call that X. And if this entire distance is 6, then from P to V, we can say, well, that is 6 minus X. And you could label it either way. I could switch where that X and 6 minus X value are. It works out a little easier if I have X as the distance from L to P. So, since I know that from L to P is X and from P to V is 6 minus X, I also need the distance from J to P. And I need that in terms of X. So again, we can use our Pythagorean theorem. And remember, the sum of the squares of the two sides is equal to the square of the hypotenuse. Or we can say 2 squared, which is 4, plus x squared equals the hypotenuse squared. So that's why we put that square root in there. So in this situation, we're going to need to calculate Jane's time from J to P and then also her time from point P to point V. So remember that distance equals rate times time, or time is going to be equal to that distance divided by rate. Okay? So time in terms of x, so along the path from J to P, the distance is the square root of 4 plus x squared divided by her rate. And from J to P she's rowing, so her rate is 2 miles per hour. Plus our distance from P to V, which is 6 minus x. And in this situation, we are traveling at 5 miles per hour. So this represents the time equation in terms of x that we want to optimize. So if we want to optimize something, we're going to take the derivative, set it equal to 0. So in order for me to take my derivative here, I'm just going to clean up the way this looks. T of x is 1/2. 4 plus x squared is going to go to the 1/2 power, plus 1/5, 6 minus x. So t prime of x, I'll use my chain rule. The 1/2 stays in front, and I end up with 1/2, 4 plus x squared to the negative 1/2. And then remember, because we're using the chain rule, we're going to need to multiply by the derivative of my inside here. And the derivative of 4 plus x squared is 2x. So then my second piece there, that 1/5 can stay in front, and the derivative of that interior 6 minus x is just -1. So moving along as I look to tidy this up, I've got 1/2 and a 1/2 and a 2. And that x can go in the numerator. So what I'm going to say here is t prime of x. The 1/2 times 1/2 is 4 with a 2 in the top. I end up with x over 2. 4 plus x squared to the negative 1/2 minus 1/5. And that negative 1/2, I can put that in the denominator as well. So t prime of x equals x over 2 square root of 4 plus x squared. The negative pulled it into the denominator, and that 1/2 power represents a square root. So this is my derivative. And in order to maximize or minimize a problem, we want to solve that derivative equal to 0. So 0, if I set this equal to 0 and I have all of this over here, x divided by 2 times the square root of 4 plus x squared minus 1/5. I'm going to add that 1/5 to the other side of my equation, and I'm going to save a little space. I'm going to move that 1/5 over here. So I've set it equal to 0, and now I've started solving. And once I move that 1/5 over, I can see that this is a proportion. And with proportion, we can cross multiply. So I have 2 square root of 4 plus x squared is equal to 5x. I can square both sides of my equation. Squaring both sides of my equation here, that will cancel my square root. Square the 2, I've got 4. And then the square root is canceled by that square. So I have 4 plus x squared equals 25x squared. Distribute 16 plus 4x squared equals 25x squared. Subtract that 4 over. I have 16 equals 21x squared. Divide by 21. 16 over 21 equals x squared. And then you square root. So I end up with plus or minus the square root of 16 over 21 equals x. And because x is a unit of measure or distance, and we're not traveling a negative distance in this situation, I can say that x equals only that positive value. Square root of 16 is 4, and I still have root 21 in the denominator. So x equals 4 divided by the square root of 21 miles. I wrote feet there, but our unit on distance in this situation is miles, which means that x is approximately 0.87 miles. So what this means to us is that Jane is going to row her boat approximately 9/10 of a mile down the coastline from where she's situated, and then she's going to get out and walk the remaining 5.1 miles. Recapping what I did here once I had my derivative. So this was my derivative. And what we wanted to do was take that derivative and let it be equal to 0. So I set it equal to 0, and then I took that negative 1/5 and moved it to the right, which gave me this proportion, and then I solved by cross multiplying. All right, so I'm going to go to the next page so we can talk about this in a cleaner space. So here is a skeleton of our diagram we had on the first page. And what we're saying is Jane isn't going to row directly to shore. She's going to row to shore a distance p away. And we set that p value between L and P, that distance was x. So x is equal to 4 over root 21. So she's going to row to that point, and at that point she's going to get out of her boat and continue walking this distance, which was 6 minus x. So that value from P to V is 6 minus 4 over root 21. And I could use the decimal approximation here, but we want to keep this very exact, so we're going to plug it in like that. So if we go back to our original time equation, time in terms of distance x, remember we had that distance over the rate, which gave me time, the square root of x squared plus 4 over 2 plus, from p to v, 6 minus x over 5. So we need to plug our x value in here. And so if I let x be 4 divided by the square root of 21, then the time it takes Jane to get to the coastal village when she rose to a point, 4 divided by root 21, approximately 0.87 miles away from where she is, would be the square root of 4 over root 21 squared plus 4 divided by 2 plus 6 minus 4 over root 21 divided by 5. And if we calculate this in our calculator, using that exact value, 4 over root 21, our calculator is going to give us an approximation of 2.116515139. So that means that if she were to row to this point, her total time is approximately 2.12 hours. And if we go back and think about our two values we had at the beginning, we said it would take Jane 2.2 hours to row directly to shore and then walk the 6 miles, versus it would take 3.16 hours for her to row straight downstream. So the distance here from J to L and L to V, we said on the last screen that took 2.2 hours. And then the distance straight from J to V, that took 3.16 hours. And you can see our value here, rowing from J to P and then P to V walking, gives us a least amount of 2.12 hours.